And as you know that okay, so let's move ahead. So again, entropy is a little complicated topic. A lot of confusion there is about entropy. Okay, so we will try to simplify it. I have, divided the topics into several sections. I have summarized the topic at the end so that you will get a clear picture of what is entropy and what and which formula to use, and which formula is basically applicable for a certain, type of question. Okay. So in the last, I know that there will be some doubts that you will have during the session, and till the end we will discuss so many formulas that you will get confused when we will use this, when we will use that. But at the end, I have given you some summary slides. Okay, so that will clear, I think, almost all of your doubts about the formulas. Okay, chalo. So now, just 1 second. So basically, entropy is what? Entropy is anyone who can tell me what is entropy? Just basic idea about entropy. Whatever you know. What do you think is entropy? What have you learned till now, or what have you heard? Entropy is randomness of molecule. Yes, freedom of molecule, or what else? Disorderedness of molecules, right? And how does this? Yes, order of disorderedness. No, measure of disorderedness. Okay. So, how does this disorderness come from? Where from it come? Where it comes from? Sorry, kinetic energy increase. You can say that, yes. So more number of collisions between molecules. Okay, so basically randomness of the molecule, or the measure of randomness or disorderness, is called as, yes, yes. Yeah, when you give energy, some energy is basically converted into entropy as well. Okay, it is basically lost energy. Entropy is a lost energy. Okay. Now, you see, whenever a thermodynamic system undergoes a process, the randomness or disorderness of the system may increase, decrease, or remain constant. Whenever, whenever any system undergoes any process, so its entropy changes. Now its entropy may increase, its entropy may decrease, or it may remain constant. Okay, so everything we are going to see when it is increasing, when it is decreasing, when it remains constant. Now, it is the second law that gives you a quantitative measure of randomness in the form of entropy. In the form of entropy. Now, how do you visualize this randomness or disorderness? Now you see, look, it is bunch of soldiers, and during a parade or during an external, when you apply some external, like when like again, I just 1 second. So basically, when you apply external force, or when you visualize the process, then the disorderness is always less. Okay, so this is basically when it is under supervision. This is under supervision, but but now nobody is supervising them. Now nobody have like any control over them. So after some time, if you just leave them as it is, after some time you will see, I mean, again, it's a symbolic picture, but what I'm trying to say is, they will not be arranged in an order. Okay, this is ordered. This is ordered formation. But if you have no control, if you have no supervision, if you let them be, so naturally or spontaneously, what will happen? Naturally, what will happen? They will move somewhere randomly, and eventually they will lead to this stage. Okay, again, it is a symbolic picture. Don't take it literally. Okay, what I'm trying to say is an ordered state is more effective. It is more effective. But when you when it when this ordered form undergoes a process naturally, then it goes to disordered form. Disordered. Or here you see here randomness is high or low. Here randomness is high or low. Yes, here randomness is low. But when when this system, if I assume this is a system, and when I leave this system to do a natural process, so after the end of this process, the randomness increases. Randomness, random. Okay, just 1 second. Randomness increases. So you see, after any natural process or naturally, whenever a system goes through a natural process or a spontaneous process, its randomness increases. So it becomes less effective. It becomes less effective. Okay. After a process, when its randomness increases, it becomes less effective. Now also you see it if it is a bunch of books. Now someone has put enough work to arrange this book in a very particular order. So here the randomness is really low. Okay. So this system is very effective. If you just walk into this library and you know that you want this book, for example, you want the book, for example, The Alchemist. Okay. So what you will do, you know what kind of genre it is. You will go to that genre. You will, and then alphabetically you can choose this particular book. But now, if I leave you in this library for 1 year without any supervision, so naturally, what will you do? You will pick up a book, throw it somewhere. You will pick up another book, throw it somewhere. So after 1 year, naturally, what will happen? Spontaneously, you will come from this stage to this stage. So again, naturally, one process is happening naturally, and randomness is increasing. So here, randomness has increased. Randomness has increased after a natural process. Now, if you go against nature, so it is a non-spontaneous process. So if you go back from here to here, you have to do a non-spontaneous work. And by doing a non-spontaneous work, you can reduce the entropy. So when you do external work, sometimes you can reduce your entropy. Okay. So again, randomness is basically it increases the disorderedness or it reduces the effectiveness of that energy. For example, you have some energy at a particular temperature. So if this energy has lower entropy, then it is more effective. More effective means you can take more work output out of that. It is able, this energy, the energy with lower entropy or lower randomness or lower disorderness will be able to give you higher work output. The energy lost will be low. Okay. But now what you do, let us say you do some, it undergoes a process. Okay. Then now here you have taken out some work, but after this process, its randomness or entropy increases. That means now you cannot, because randomness has increased. Higher entropy means less work output. Okay, less effective energy, less effective system. If I say a system has higher randomness, that means the molecules are very randomly arranged. There is no particular order. There is very high disorderness, and therefore it's really difficult. So randomness is what? Look, this is one system, and all the molecules are arranged like this. Maybe little bit this, little bit like this. Okay. So basically they are all arranged in a particular order. But if you have a system, something like this. So one molecule is like this, one is like this, one is like this, one is like this, one is like this. Okay. So here molecules are very randomly arranged. So this is higher randomness, means higher entropy, means less effective energy. Here randomness is low. So when you measure this randomness in a quantitative term, then it is called as entropy. So entropy is the measure of this randomness. So higher entropy means higher randomness, less effective energy. Less effective means you can have less work output out of that. Okay. So for example, if you have 100 units of energy at 1000 Kelvin and you have 100 units of energy at 500 Kelvin. Okay. So this, because the temperature is higher, the same amount of energy will give you more work output. This work output will be higher. This is Q out. Okay. This is Q in. So this energy will give you less work output compared to this one. Here temperature is low compared to this one. Amount energy is same. Energy is same. So when when any energy gives you higher work output, it is more effective. Basically, you are able to extract more useful work out of it. So if this work output is more, that means Q losses will be less anyway. Okay. And here Q out will be more. Got it? This is basically second law tells you that the energy at higher temperature is more effective. Okay, and I think we proved this as well somewhere, although I have not covered it. And let me just give me 1 second, and even this one tells you, see, Q1 by Q2. Okay, okay, yeah. Let me just explain this once again. Okay, so you see, do you remember your Carnot engine? Okay, so okay, okay. Abhi, we have not studied entropy, but let me just give you some idea. So this is TS diagram. Till now, we have only discussed about PV diagrams, right? But in Carnot cycle, we have seen TS diagram. So what was the TS diagram in Carnot cycle? This was your TS diagram. Yes, remember? Yes. Now, see, this is some temperature. This is some temperature, 1000 Kelvin. Okay. Now, this 1000 Kelvin, how much work it can give you? So, what is work? Work is basically the 1 second. Let us say this is your 300 Kelvin. Okay. So, this area enclosed by this cycle is work output, network. Okay. And it is also equal to Q net. Can you make sense out of it? Can you make sense out of it? You see, yes, no. Then I'll explain more. Yes. Okay. So W net is equals to Q net. Why? Because you see, this is your Q in. This is your Q out. I hope you remember this diagram. And this is W out. This is W in. Now, if you go to first law of thermodynamics, so I think you will, let me explain it more elaborately so that any doubt could be cleared. So this is your TS diagram. And if you remember, it was like this. Okay, assume it is a horizontal line. I see it can, it had some slope, but this I assume it is horizontal line. Okay. Now, if you remember, this was your Q in. Okay. So anything below this curve is basically your Q in. Everything below this curve is Q in. This much heat you are giving to your engine. Okay. Now, anything below this is Q out. So this is your Q out. What is your Q out? This is your Q out. Yes. So what is this? What is this area under this cycle? It is Q net, which is also equal to Q in minus Q out. Yes. Okay. Now, from first law, of thermodynamics, for a cycle, what do we, it is a cycle, right? Carnot cycle. What do we understand? Summation of Q is equals to summation of W. Yes. So Q net, this area which is Q net, it is also equal to work net. Where, if you remember, this is your work turbine, which is work output, and this is your work input. So this area is also telling you net work as well, which is W output minus W input. This much is clear, yes or no? Now, coming to your question, that you see now this let us say this temperature is equals to 1000 Kelvin. Okay, and this is your, as I said, surrounding temperature should be the temperature at which you are rejecting heat. Yes. Now, if your surrounding temperature will remain fixed, okay, lower temperature, this is higher temperature. So if, let it remain fixed. Now the work output is basically area enclosed. Okay. So this, all this is your work out, the net work. Okay. So if T higher is equals to 1000 Kelvin, then the work output, work net is basically the blue color, this black color, sorry. Now, if you take this heat is transferred at some lower temperature. Let us say you are transferring heat here. Okay, same heat you are transferring. Q in is same amount of heat you are transferring at, let us say, temperature is equals to 500 Kelvin. Then tell me what is the work network. So now this area is network. This area is net work. So if T higher is equals to 500 Kelvin, then net work is this. Okay. Now can you see by the diagram, net work when temperature is higher is greater than, yes, yes or no? Yes. So that is basically telling you that when you supply same amount of heat at higher temperature, you can get more work output. And that is the reason that heat supplied at higher temperature is more effective. Got it? So if you reduce the temperature, your work output reduces. You are supplying same amount of heat. Q in is same, but your work net is reduced. So what will happen? Your Q out will increase. So a lot of energy is wasted here. You see, a lot of energy is wasted here. Abhishek, did you get your answer? Okay, so let's move ahead. Okay, so I hope you understand what is entropy. Entropy is the measure of randomness. Okay, and randomness is what? Randomness is basically when the molecules are very randomly arranged. It is a less effective energy, and basically, so it's like less effective, and the measure of this randomness in quantitative term is called as entropy. Okay, I hope this much is clear. Now, the first thing that is explained about entropy is Clausius theorem. So Clausius theorem basically tells you that for a Just 1 second. Yes. So Clausius theorem tells you that for a reversible cycle, cyclic integral of dq by t, reversible, okay, only reversible cycle I am talking about, only reversible, is equals to 0. So for a reversible cycle, this ratio dq by t is equals to 0. Now you tell, if you remember, tell me cyclic integral of what is equals to 0. Do you remember this? We have discussed cyclic integral of what is equals to 0. Yes, so cyclic integral of any property is equals to 0. So basically, this is one term, dq by t is one term, which is dependent. Yes, that is a point function. Yes. So this depends on the heat transfer and temperature of the system. Okay. This is one term that depends on the heat, how much heat transfer you are giving at what temperature. Okay. So, and we saw that cyclic integral of dq by t is 0. That means this term is a property. This term is a property, and we gave this property a name called as entropy. So this property is basically what dq by t. Okay, and we have given this name as entropy. So entropy is a property. Okay, entropy is a property, and the cyclic integral of dq by t is equals to 0. So basically, for a cycle, for a reversible, again very important, reversible cycle, entropy is how much? Change in entropy. For a reversible cycle, change in entropy is equals to 0. Is equals to 0. Okay. So this is your Clausius theorem. And again, we are only talking about reversible cycle, not irreversible. Only reversible cycle. Okay. Now, so mathematically for a reversible cyclic, ds is equals to dq by t. And when we talk about cycle, this ratio or ds is equals to 0. Okay. Now rearrange this equation? So dq is equals to tds. dq is equals to tds. Okay. Now if you remember, we have defined what? dw is equals to pdv. Similarly, we have defined work for open system is equals to minus vdp. So, and you have seen that, PV diagram of it. By the same logic, I don't think I need to explain it more. I can draw a TS diagram. You see, this is PV diagram we draw to explain work transfer. Here I can draw TS diagram, and I can take a very small temperature, and I can take a change in entropy here. Similarly, I can do it infinite number of times, and I will get this area under the curve. Okay, so this area under the curve is basically what? This area under the curve is integration of small temperature and ds, which is equals to, from this equation, dq. Okay, so dq, heat transfer is given by the area under the curve. Okay, heat transfer is given by area under the curve on TS diagram. when extended on entropy axis. Okay, this is what heat transfer gives you. Heat transfer. Okay, so you can also understand this by our, this diagram as well. You see, this is the curve. If you say this is the curve, this is the curve, and this everything below it is give on the entropy axis is giving you this heat transfer. Okay. Similarly, area under this curve, this is giving you Q out. This is giving you Q out. So heat transfer is given by the area under the curve when extended on the entropy axis. Okay. I hope that you can also tell me how we can show the closed system work transfer on PV diagram. So what is that area? Do you remember? Work transfer for closed system. Area under the curve on what axis? Closed system on volume axis. Yes. How about open system? How about open system on pressure axis? Yes, area under the curve when extended on pressure axis. Very nice. I'm happy to see that you remember things. So this will not be very difficult for you, okay? Because I mean, we had the same kind of equation, right? So I don't think it needs any explanation. Okay. Now, specific entropy is basically entropy divided by mass. Now, I have already explained you entropy is a property. Because it's cyclic integral, we have seen is equals to 0, and therefore it is a point function. Now, dx again, change in entropy is an exact differential, and therefore again it is a property, it is a point function, and therefore it is independent of the path taken by the process. Okay, but it is an extensive property and has the unit kilojoule per Kelvin, kilojoule per Kelvin. Okay, now Clausius inequality. Clausius inequality. So it basically tells you that dq by t for a cycle is always less than equal to 0. You see, when I told you earlier, what did I say? I said that for a reversible cycle, dq by t is equal to 0. dq by t is equals to 0. For now, Clausius inequality is an extension of Clausius theorem. Okay, it includes dq by t for reversible cycle as well as irreversible cycle. Okay, so reversible cycle I have discussed in Clausius theorem, but here for a cycle, this is what we have already discussed. Clausius theorem has told you that for a reversible cycle, cyclic integral of dq by t is equals to 0. And therefore, I can say change in entropy is equals to 0. Because what is this? This is entropy. Okay, ds. Now, if you have an irreversible cycle, but a possible cycle, okay, then it's this cyclic integral of dq by t is less than 0. So cyclic integral of ds is less than 0. Is less than 0. Okay. If it is an impossible cycle, then cyclic integral of dq by t is greater than 0. So it is a very important objective question that when do you say the cycle is impossible? So look, I was telling you when I started the second law that first law limitation was this, first law limitation was that, but it is the second law that explained you things. Okay, so this is one application of the second law that it will first law will, I mean, I can come up to you and say that this is what I have designed for you, and first law will do energy conservation and tell you, okay, it's fine. But then if you check this ratio dq by t, and if it is greater than 0, then you will understand that this cycle is not even possible. Okay, so it has put a restriction on the cycle. Similarly, for a process also it puts a restriction. Later on we will see. Okay. So this is the way that second law aids to the property of first law. So first law tells you energy conservation. You do energy conservation, you move ahead. But that is not giving you the full picture. You have to check that is this condition satisfied or not. So if it is greater than 0, that means it is impossible. So either it should be 0, then it is a reversible cycle, or it should be less than 0, then it is irreversible cycle, but it is still possible. It is still possible. But this is impossible cycle. This is impossible cycle. Okay. So you see, for example, like if I come up to you and say that I have designed this engine in which I am giving you some Q1 and some work output is getting, okay, and Q2. Now I'll say my efficiency is what? Let us say 15%. So first of all, I'll do energy balance. So energy balance is Q1 is equals to W out plus Q2. Let us say it is satisfied. Let us say it is satisfied. Okay. Then I'll further go one step ahead. I will do cyclic integral of dq by t. So what is this? Q1 is going inside. Okay. So it is positive. Q1 by T1 plus Q2 is going out. So I will take minus Q2 kahan pe? At T2. So if this summation comes greater than 0, so I will say that it is an impossible cycle. Even though first law is satisfied, but this cycle is not possible. Okay, got it? Yes or no? Okay. Now, what about the process? So process, you see, the cyclic integral of dq by t is equals to cyclic integral of ds. But for a cycle, it is 0. But when I only talk about process, so it is basically equal to this. Okay. Here it is, ds is not 0. So simply for a process, ds is greater than equal to dq by t. It is greater than equal to dq by t. Okay. No, this is, what is this? It is a reservoir, right? So its temperature will remain fixed. Okay. Its temperature will remain fixed. In this particular case, but if the temperature is changing, we will talk about that in some time. Got it? But in this particular case, we are talking about thermal energy reservoir, right? Temperature will remain same of the reservoir. Got it? When the temperature is changing, we will talk in some time. Today only we will talk. Okay. Chalo. So for a reversible process, it is equal to dq by t. And for an irreversible process, ds irreversible is greater than dq by t irreversible. So basically, entropy in a reversible process is greater than dq by t irreversible. Now you tell me one thing. What is dq by t? What is the? I have told you it is a property. Yes. Yes or no? Okay. Now, dq by t is a property. dq by t is a property, and therefore it does not depend on the path, right? If it is reversible path or irreversible path, this ratio of dq by t will not change as long as the initial and final conditions are same. Initial and final conditions are same. Okay. So it doesn't matter. I can directly write ds irreversible is equals to cyclic integral of dq by t simple without any reversible irreversible, because it does not matter. Okay. But you see, this left hand side is greater than right hand side. That means if I am putting is equals to here, then I have to add something here, and that is entropy generation. which comes because of the irreversible process. So this is generating inside the body. Okay, so here we say this is what? External. This is external irreversibility. This is external irreversibility. This is internal irreversibility. Okay, these are two terms. So for an irreversible process, total entropy is basically dq by t plus entropy generation, and this is called as external irreversibility. This is called as internal irreversibility. Okay, so how do you explain external and internal irreversibility? Like this. So the entropy of any system, any closed system, can increase in two ways. The first is external irreversibility. So this is the irreversibility that is external, means external of what? For example, you have this system. Okay. Now, when I am transferring some heat from outside, so this is what? It is an external interaction. It is coming from outside. So the entropy that will be occurred because of this external heat transfer is called as external irreversibility. So how do I explain this external irreversibility? Change in entropy because of external irreversibility is equals to, I can say, dq by t. dq by t, cyclic integral of dq by t. Okay. Now what will be happening is, you see, it is coming from outside of the system. Now, inside of the system, there will also be some processes going on. For example, piston is moving. For example, there is some friction, some other rotational, rotary parts or something else. The most common phenomena of internal irreversibility is friction or viscosity. You see, there are fluid layers inside. So when these fluid layers are flowing one over the other, there is viscosity. So that is also a friction. There is a resistance there. Okay, so basically whatever is happening inside the system and any irreversibility is coming because of that. The most common phenomena is friction. Okay, because friction is happening inside the system. So because of that, whatever entropy is added is called as internal irreversibility and is termed as entropy generation. Okay, it is generated, entropy generation generated inside the system. Okay, so here this is internal irreversibility and it is expressed as entropy generation. So the total entropy for an irreversible process is dq by t, irreversible or reversible, as I told you, doesn't matter, but plus entropy generation. So for a reversible, now you see, for a reversible process, I assume there is no friction, no viscosity, and therefore I can say entropy generation is equals to 0. So ds is equals to cyclic integral of dq by t. And that is what we defined earlier as well. So you see, for a reversible process, this portion is 0. It only comes when we talk about irreversible process. And it comes because of the irreversibility inside the system. For example, friction, turbulence, electrical resistance, magnetic hysteresis, or viscosity also. Okay, so now you see, though entropy is a property, entropy generation is not. Okay, this is because you see, it is basically irreversibility. Okay, so it depends on the path. It depends on the path. Okay, so entropy generation is not a property. It's a path function. And entropy generation is always positive. Always positive means what? Or either it is 0 for reversible or it is going to increase. Because friction will always keep adding to it and entropy generation will always increase. So it is always greater than equal to 0. And for a reversible process, entropy generation is 0. For a reversible process, entropy generation is 0. Okay, so is this clear? Yes. So many formulas we are going to discuss today, but I can't do anything about it. What I can do is I can summarize them for you, which I have done in the end, and that will reduce a lot of work for you. Yes. So you see, look, now we have a system. Look, total entropy is equals to entropy because of heat transfer plus entropy generated inside the system. Okay. Now you see, this is called as entropy transfer. This is entropy transfer. This is entropy generated. This is called as external irreversibility. This is called as internal irreversibility. Now, you see external. So any irreversibility that is coming from outside is called as external irreversibility. Now, if you have a system, okay, so heat transfer, I have already told you, heat transfer only happens when it crosses the boundary. So if heat transfer coming from outside to inside, so you are doing some heat transfer dq, right? And it will be happening from a certain, for example, your outside temperature is 30 degrees Celsius. Okay, so that is your T. So dq by T is bringing some irreversibility inside the system. But from where? From outside. Okay, when this, when this heat transfer is happening, some irreversibility or entropy is changing inside the body. And why is it happening? Because of this heat transfer. And where is this heat transfer coming from? From outside. Okay, from externally. And that is why it is called an external irreversibility. Now, inside the system, there could be friction. Okay, for example, piston is moving up and down, so friction is happening. Or, for example, fluid is there, water is flowing, or some fluid is flowing. So, when fluid is flowing, there is a viscosity between two layers of this fluid, right? So, that is also a kind of irreversibility, but it is happening inside the system. It is not coming from outside, it is generated inside the system. Okay, so whatever is entropy that is increases because of this friction or viscosity is called as entropy generation, and because it is happening internally, so it is called as internal irreversibility, and the entropy increases because of this is called as entropy generation. Is it okay? Okay, so let's move ahead. Yes. Okay, now now be very cautious. Now be very cautious, because now we are starting the formula. Then there will be a lot of formula. I am already telling you. So make up your mind already for that. Okay. But I have divided the formula in such a way that, and I will try to explain it in a way that it should be very clear which formula is applicable in which case. Okay. Chalo. Now, entropy change in a system undergoing a reversible process. So we are talking about entropy change in a system, first of all. Mark the words, in a system when it is undergoing a reversible process. So two points are very important here. System and reversible process. Okay. So you are going from I to F. Okay. But how are you going? And you are doing a reversible process. Okay. But you are doing reversible isothermal heat transfer. Reversible isothermal heat transfer. What is an example? For example, you have a thermal energy reservoir. Thermal energy reservoir. And you are transferring heat at this particular temperature. So for example, whatever heat you have transferred, so now the entropy of this thermal energy reservoir will change. Okay, the entropy of this thermal energy reservoir will change. How much it will change if you need to calculate? So this time, what is this? This is your system. This is your system. So this is your system, you see, and this heat transfer is reversible. So this is also satisfied. And you are talking about isothermal heat transfer, isothermal heat transfer. Okay. So if all these conditions are satisfied, again, mark my words, you have a system that is undergoing a reversible process and isothermal heat transfer is happening, isothermal heat transfer. Okay. So what will happen? You see, the general formula is ds is equals to integration of dq by t. Okay. So this is your general formula. We will always start from here, first of all. Then we will move based upon what is our system and what are the conditions. Now, be very cautious about the next step. Okay. I have told you it is isothermal heat transfer. It is isothermal heat transfer. That means temperature of the system is constant. So if temperature of the system is constant, I can bring out temperature. And the only thing I have is dq. Okay, from 1 to 2 or I to f. Okay, so simply if you know, like for example, whatever you are doing, you are transferring some heat here, q in, so you can write q in minus 0 upon temperature. So basically q in by temperature. So if you need to calculate the entropy change of this thermal energy reservoir, you can simply write whatever heat is going out, q upon, so let us not write q in because it can be q out as well. Okay, so it's simply q. Okay, so q upon whatever temperature of this thermal energy reservoir is. So you can find out the entropy change of a system undergoing a reversible process when a reversible isothermal heat transfer is happening. So you can find out ds is equals to simply dq by t. You do not have to integrate here. Okay, so whatever heat is getting out or in, you can write in the numerator, and temperature is already constant, so you can directly calculate your entropy change. Is it clear? Only one case we have discussed till now, and there will be many cases. Okay, so if the temperature is constant, then what will you do? You can directly write dq by t, dq by t. ठीक है, clear? Shivendra Raj, thermal energy reservoir, I have explained in the last class. We had a whole discussion. Okay, so please go through that. Before we started the statements of second law, I have explained it very clearly. Okay, can everyone agree with me? I have explained this right, or I am missing something? Okay, okay, because Shivendra, I can explain. I mean, I can briefly explain, but basically I have to cover a lot. Okay, and just to give you a brief, thermal energy reservoir is a reservoir. It is a reservoir first of all. Okay, reservoir means plenty of things that can be there. So it is a reservoir with of thermal energy. So it can transfer you energy, infinite amount of energy, and not infinite. It can transfer finite amount of energy and also absorb finite amount of energy without any change in its temperature. Its temperature will not change. Okay, Baki, you can go ahead and just, I have explained it very elaboratively, so you can see. Now let us come to the case 2. Again, first of all, remember case 1, reversible isothermal heat transfer. Okay, now case 2 is, okay, so case 2 is reversible non-isothermal heat transfer. Reversible non, so now the temperature is changing. Now the temperature is changing. So for example, if you see, this is one body and it is transferring some heat So if the temperature was earlier T initial, because of this heat transfer, its temperature is changing. Its temperature is changing. So this is your initial temperature T initial. This is your final temperature. And some heat transfer is happening. Q in or Q out is happening. Okay. So if these kind of systems are there when there is non-isothermal heat transfer, then what will you do? What will you do? So now this time you see ds is equals to dq by t. ds is equals to dq by t. Now here temperature you cannot take out. Temperature you cannot take out. So what will you do? What will you do? So basically I have to convert it in a form in properties. Basically I have to convert dq in the form of properties, and then only I will be able to integrate it. Okay. So there will be two cases here for reversible non-isothermal. It will be solids and liquids, and it will be ideal gas. Okay. So let us start with solids and liquids. So as I said, so again remember we are still talking about system and reversible process, but what case? Non-isothermal heat transfer. Okay. So now if you remember, dq for solids is equals to du plus d or dh is equals to mc dt. Solids and liquid, we have discussed this, yes? Do you remember? dq is equals to du plus pdv, dq is equals to dh minus vdp. So this got cancelled, and dq is equals to du is equals to dh as well. Remember? Yes or no? We have discussed this for solids and liquids when we were talking about heat transfer in that particular session. I have discussed this. Yes. Okay. So dq is equals to mc dt. Now I can substitute dq here. Okay. So ds reversible. Look, now I cannot take temperature out. You see, because temperature is not constant. So I will write mc dt by t. But mass and specific heat is constant. So it is dt by t initial to final. So basically mc ln t final by t initial. Okay. So if we have a system that is undergoing a reversible process, and what kind of process? Non-isothermal heat transfer is happening, and we are talking about solids and liquids. So you can calculate entropy using this formula. Got it? Kilojoule per Kelvin. Yes or no? Everyone, is it clear? Okay. What will happen if we have an ideal gas? Now, ideal gas dq is equals to, this is my general equation. This is first law for closed system. This is first law for open system. So I have to put it one by one. Once I'll put this, then I'll put this. I will get two formulas, and depending upon what is given to me in question, I can use either of them. Okay. There is no right or wrong formula. If you have an ideal gas, okay. If you have a system that is undergoing reversible process, and what kind of process? Non-isothermal heat transfer. And you have an ideal gas. So you can use these two formulas which we are going to define now. Okay. So let us define first one. So let me substitute this dq here. So I can write ds is equals to du plus pdv by t. Okay. So du is equals to mcv dt by t. How about p by t? So you see, what is you see we have ideal gas. So if we have ideal gas, I can write PV is equals to mRT. So P by T is equals to mR by V. So I can write mR dV by V. dV by V. Any doubt in this step? Anyone? By du is equals to mCV dt and P by T is equals to mR by V. Any doubt, anyone? Only one answer is there. How about everyone? Is it clear to everyone? Okay, okay. I want more. I want more answers. Okay. Is it clear to everyone? Okay. So now I can integrate MCV initial to final. So ln T final by T initial plus MR ln V final by V initial. Okay. So this is your capital DS. I can also write it in the form of small ds is equals to CV ln T final by T initial plus R ln V final by V initial. Okay. The unit here is kilojoule per Kelvin. Here it is kilojoule per kg Kelvin. Okay. So this is your first formula. Now I think you will be able to easily define the next formula. Okay. So if you have this, you can substitute it here. So ds is equals to dH by T plus, sorry, minus V dP by T. Okay. Now what is dH? M Cp dt by T minus V by T. So PV is equals to mRT. V by T is equals to mR by P. So I can write mR dP by P initial to final. Initial to final. MCP ln T final by T initial minus mR T final by T initial. Okay, so this is your capital DS. Its unit is kilojoule per Kelvin. Now you can also write this in the form of small ds. Okay, so mass you can remove. CPln T final by T initial minus M minus R ln. Okay, this I ln missed. Okay, ln P final by P initial. Okay, and the unit here is kilojoule per kg Kelvin. Okay. So now for ideal gas you have two formulas. Ideal gas you have two formulas. One is this one and the other is this one. Now when would you use which one? So if temperature and volume is given, you will use this one. If temperature and pressure is given, you will use this one. Okay. Got it? Got it, everyone? Any doubt, anyone? This one? This one. So are we clear, everyone? Are we clear till now? I know there are quite few formulas, but I hope we are clear. Okay. Now, now let me give you a brief history what we have done till now. Then we'll come back. I don't want to, burden you with all these formulas. Okay. So Clausius inequality, we have seen that for a cycle, dq by t is always less than equal to 0. So if you have reversible cycle, cyclic integral of dq by t is equals to 0. If you have irreversible cycle, cyclic integral of dq by t is less than 0. For a process, ds is greater than equal to dq by t. So if you have a reversible process, then ds is equals to dq by t, and if it is irreversible, then it is ds is equals to dq by t plus entropy generation. Okay. Now entropy change of a system. If you have a reversible isothermal process, okay, reversible isothermal process, then for example thermal reservoir could be there, or also phase change is happening. Means phase change means heat transfer is happening but the temperature is same, then you can use this formula. But if you have a non-isothermal heat transfer, I am sorry, non is missing here, non-isothermal heat transfer, then if solids and liquids are there, you can use this formula, or if it is ideal gas, you can use any of them. Okay. So this is what we have discussed till now. Got it? Now, let us move back. So, next is increase in entropy principle. Increase in entropy principle. So it basically says that the entropy of an isolated system. Now, what is an isolated system? It is universe is an isolated system. So the entropy of an isolated, and what is universe? Universe is basically system plus surrounding. Okay. So the entropy of an isolated system can never decrease, It always increases or remains constant only when the reversible process is reversible. So it is called as principle of increase of entropy or entropy principle. So simply it is telling you that change in entropy of the universe is always greater than equal to 0. And there are a lot of psychology also which goes behind this. Okay, so this is what we have been seeing, all the processes that we are doing on a daily basis. I'm not talking about power plants working, and I'm not talking about very energy intensive processes. Whatever even we do in our daily life, from moving of our hand, or from cooking our meal, or from doing anything. So whatever we release some heat, or we include or there is some friction involved that. Okay. So because you see entropy of the system is equals to 0 when if you have a reversible, for example, a reversible process there. If you have a reversible process, which of course there is no reversible process. So change in entropy of universe will be equal to 0. Okay. But if it is an irreversible process, then ds of universe is positive. It is greater than 0. It is always increases. So whatever you do in a daily basis, even from moving your hand to cooking your meal or anything, or just walking, you are increasing. Basically, you are doing a process. Okay. So while doing that process, some heat is getting released, and that heat is going to the surrounding, and that is basically increasing the entropy of the universe. Okay, so entropy of the universe is continuously increasing, and therefore the entropy of the universe is continuously increasing. So basically, there will come a time that you will have all the energy in the world, but the quality of that energy will be very low. So you cannot extract any work output out of that. So what will you do? You will have to use more energy intensive processes. Okay. So basically, this is, like an entropy is a very psychological concept as well. Okay. So, but yeah, I mean, entropy of the universe is always increasing, which is actually not good. Okay. There will come a time that entropy will be so high and the quality of energy is so low that, I mean, like basically we will not be able to utilize that energy in any way. Okay. So now, the increase in entropy principle tells you that the entropy of universe is always greater than or equal to zero. Okay. So now, as I told you, you can say entropy of universe or entropy of system plus entropy of surrounding collectively added is what? Universe. Okay. Or what is process? Process is also system plus surrounding. Okay. So when a process happening, both the system and surrounds gets affected. Okay. It is always greater than or equal to zero. And this is your increase in entropy principle. Okay. Now, entropy change of the system. You see, I have told you in the very beginning, the first uh, statement I read was whenever a process happens, entropy of the system may increase, decrease, or remain constant. In entropy of the system, you see, I am telling you one thing here. Entropy of the universe means system plus surrounding, is always positive, means it always increases. Now, after universe, I have come to a particular system, entropy change of a system. So if you have one system and it is interacting some heat with the surrounding, then how will the effect, what will be the effect on the system? Okay. So first of all, let us talk about reversible processes. First of all, let us talk about reversible processes. So as we know, entropy generation or internal irreversibility is equals to zero. So this is zero. Only external irreversibility is there for reversible process. So this is our formula for reversible processes for a reversible system. Okay. Now, if I am adding heat, let us say I am adding heat, then what will happen? So you see, ds is equals to dq by t. Now you are adding heat, means numerator is increasing. That means entropy is also going to increase. So in this case, I can say ds is greater than 0, or I can say S2 or final energy is greater than initial energy, and therefore entropy is increasing. Entropy is increasing. Okay. Now, when your entropy of the system is increasing, so whenever you are adding heat to a system, whenever you are adding heat, so you are adding heat to a system, so this system's entropy will increase. For reversible, right? I have explained, no, for reversible, there is no friction, there is no viscosity, reversible processes. This internal irreversibility is generated due to friction, due to viscosity, magnetic hysteresis, resistances. But for reversible process, we assume they are all zero. So therefore, entropy generation is zero for reversible. Okay. But in irreversible process, it is non-zero. Okay. Chalo. Now, what about heat rejection? When the heat is rejected by any system, So again, ds is equals to dq by. Now you are rejecting heat. So when you are rejecting heat, dq decreases. That means entropy also decreases. So ds is decreasing less than zero. That means final entropy is less than initial entropy, and entropy is decreasing. Entropy is decreasing. What about reversible adiabatic, which is also called as isentropic? And why is it called as isentropic? Is because here you see, by it is adiabatic means no heat transfer. No heat transfer means this is zero. So basically, ds is also equal to 0 means S2 is equals to S1 means entropy is equals to constant, and that is the reason that reversible adiabatic process is called as isentropic process. Reversible adiabatic process is called as isentropic process. Is it clear? Now, can anyone tell me, here I am saying entropy is always increasing. You see, entropy, I am telling you that entropy of a system can never decrease. And here I am telling you entropy is decreasing. Can anyone explain me? Am I not contradicting myself? One place I am saying entropy can never decrease, and here I am saying it is decreasing. Can you explain me? What is the difference? Why is it happening? Anyone? Should I explain, or are you trying to say something? Should I explain? Yes or no? Chat. Just go. Give me yes or no. Should I explain? Okay. So as I am telling you, look, this is what? This is entropy of the universe. Entropy of the universe. Okay. And this is entropy of a system alone. So even though it is decreasing, so you see what is happening. Reversible heat rejection. So what is there? Let us say you have a system and this is rejecting heat. Q out. So now ds is equals to dq by t. Now it is rejecting S. So ds is decreasing. Okay. So S is decreasing. But this heat is going where? It is going to surrounding. So surrounding, it is Q added. So if I say ds of surrounding, so it is only for system. You see, for surrounding, it is also dq by t. Here, heat is added. So this is increasing, and therefore this is also increased. So S is increasing. Now, so S of system, entropy of system is decreasing, entropy of surrounding is increasing, and this will be happening in such a way that entropy of universe, which is equals to entropy of system plus entropy of surrounding. So one is decreasing, one is increasing, but the combination of the two will always increase. Combination of the two will always increase. So I'm talking about universe there. That is why I was focusing here. I'm talking about universe. And here I'm talking about only system. Similarly here, if you are adding heat, the entropy of the system is increasing, but entropy of surrounding will be decreasing, and the combination of them will always increase. You can't do anything. Okay, is it clear? Now is it clear? Okay, now next is, so Entropy change of a system undergoing reversible process either may increase. Again, I am talking about system here, and it is a very frequently asked objective question. The entropy of the system is always positive, may increase, may decrease, or may remain constant. Okay. Actually, entropy of the universe they will ask, because for system there is more than one answer. Okay. So basically, entropy of the universe can never decrease, but of the system it can increase, decrease, or remain constant. Okay. Entropy change for a reversible adiabatic process is zero, and that's why it is called as isentropic process. Okay. Now, next is irreversible process. Irreversible process. Now here you have both. You have external irreversibility and internal irreversibility as well. So dq by t irreversible plus entropy generation. And when I explain you entropy generation, I told you that it is always positive, because of friction or viscosity, it is always added. It is generated all. You see, it is generating inside the system. It is not going anywhere. So it is only generated, and therefore it is always positive. Okay, so entropy generation is always positive. Entropy generation is always positive. Okay, so now if that was reversible heat addition, it is irreversible heat addition. So it is equals to ds is equals to dq by t plus entropy generation. Now you see, you are adding heat. Okay, so you are adding heat. So because you are adding heat, so this is increasing, and this always increases. It is always positive. So basically, change in entropy will be positive. Okay, so you see, this is positive, this is positive. So ds is greater than 0, and S2 final entropy is greater than S1. So basically, entropy increases. What about irreversible adiabatic? So ds is equals to dq by t plus entropy generation. Now you see, it is adiabatic. So if it is adiabatic, this is 0, but it is always positive. That means it will also increase. So again, ds is greater than 0, S2 is greater than S1, and therefore entropy increases. So never get confused about if it is adiabatic process, it is a isentropic process. You see, it is a adiabatic process, but it is not isentropic. Here, entropy change is not equal to 0, or entropy is not constant here. Okay, it is adiabatic, but entropy is changing here. So adiabatic process does not mean isentropic process. Be very clear. Adiabatic process does not mean isentropic. Reversible adiabatic means isentropic. Reversible adiabatic means isentropic. Okay. Now, what is happening with irreversible heat rejection? So, for irreversible heat rejection, we can have, you see, ds is equals to dq by t plus entropy generation. Okay. So, we are rejecting heat. We are rejecting heat. Okay. So, ds is equals to, it is negative plus it is positive. Okay. It is positive. So, ds is equals to, because of this, entropy is decreasing, and because of the it is increasing. So what will be the overall change in entropy? So it depends which one is dominating. So you see, let us say that the decrease is less. Let us say that the decrease of entropy due to this is less, but the increase is entropy because of entropy generation is more. So here ds is positive and entropy increases. Entropy increases. But if ds is equals to decrease is more plus increase is less, so that means it is decreasing more. That means entropy is less than 0 and entropy decreases. The final case that can happen here is that the decrease in entropy will be equal to increase in entropy. So here ds is equals to 0 and entropy is equals to constant, and this is also called as isentropic process. This is also called as isentropic. So I think Abhishek or someone was asking me earlier that is I why don't we always something, I think I don't remember the exact question, but the question was, if I remember correctly, a lot of time people confuse about isentropic and reversible adiabatic. Okay, so every time they think if it is isentropic, that means it is irreversible adiabatic. No. Okay, so I can write here that not all. Okay, let me write it in some other way. All reversible adiabatic process is isentropic process, but not all isentropic process is reversible adiabatic. Okay, so isentropic can happen in two ways. If it is reversible adiabatic, or if it is irreversible heat rejection. Okay, irreversible heat rejection. So here is also entropy is equals to constant. Here is also entropy is equals to constant. So reversible process is always isentropic, but isentropic process can be either reversible adiabatic or this as well. Okay, is it clear? Is it clear, everyone? Or any doubt if you have asked? Guys, come on, reply. Is it clear, or if you have any doubt, then go ahead and ask. Okay, okay. Okay, thank you. Now, so entropy change of a system undergoing an irreversible process may increase, decrease, or remain constant. Entropy change of a system undergoing a reversible process or irreversible process may increase, decrease, or remain constant. Okay, and a reversible adiabatic process is always isentropic, but the reverse is not always true. Okay, chalo. So let us come to entropy balance. What do you mean by entropy balance? Like we used to do last slide. Which last slide? This one? Yeah, just now I explained. No, this is what the last statement is this. What I explained you, the last statement is saying this. Okay, it is saying that the reversible adiabatic process, it is telling you that reversible adiabatic process is always isentropic, but the reverse is not true. Reverse is not true means isentropic process is not always reversible adiabatic. So it can be reversible adiabatic or can be irreversible heat rejection. Okay, that is why it is telling you a reversible adiabatic process is always isentropic, but you cannot say the reverse. You cannot say that isentropic process is always reversible adiabatic. Okay, because there could be a chance that it is not reversible adiabatic, but it is isentropic. Okay. Okay. So like we used to do energy balance, we will do entropy balance. So entropy change of the system during the process is equal to, so entropy change of system is equals to total entropy entering minus total entropy leaving plus entropy generated. Okay, so I can say change of entropy of the system is equals to entropy in minus entropy out plus entropy generation. Okay, so we can apply it to closed system or open system as well. Before that, let me talk about, so entropy can be transferred to and from the system by two mechanisms. What? Heat transfer and mass transfer. Okay. Okay. So let us say you have a system. Okay. Some heat in is happening, Q out is happening, and some mass is coming in. So when mass is coming in, some entropy with mass will also come in. Similarly, when mass will go out, exit, entropy will also exit. Okay. So what is entropy in here? Entropy in is equals to Q in by T in plus Mi Si. What is entropy out? Q out by T out plus M exit S exit. Okay. So this is entropy in, entropy out. Okay. So we can apply this energy balance in a closed and open system. So entropy balance in a closed system, Now when we talk about closed system, mass flow rate is 0. You see, no mass in, no mass exit is equals to 0. So basically change of entropy of the system, which was entropy in minus entropy out plus entropy generation. So I can say Q in by T in minus Q out by T out plus entropy generation. The summation of Q by T plus entropy generation. Now this only you can use for closed system, Okay. Next is same application, but for open system, So open system, you see you have mass flow rate as well. So you can do ds is equals to S in plus S minus S out plus entropy generation. So what is energy in, entropy in this case? So this one, okay. Mi Si plus Q in by T in. Then it is M exit, S exit minus Q out, T out plus entropy generation. So I can say summation of, if there are more than one streams, so I can write this as well. Plus summation of Q by T plus entropy generation. So this is your for open system. for open system entropy balance. Okay, so is it clear? Is it clear? Okay, so let us come to the last part of today's topic. And I know I know that there are so many formulas that I have, you know, that is there in entropy, and it could be a little confusing, but if you know when to use which formula, I think you can, figure out the way to solve questions. Now, combine first and second law of thermodynamics. Combined first and second law of thermodynamics. So from first law, closed system, I hope you remember we defined dq is equals to du plus pdv. Yes. Now for open system, we define dq is equals to dh minus vdp. Okay. And from second law, we have defined ds is equals to dq by t. So from here I can write dq is equals to t ds. Okay. So now what can I do? I can substitute it here. I can substitute dq tds here and here. So now I'm combining. This is first law. There's second law. If I combine first and second law, so if I substitute this in this first equation, I can write TdS is equals to du plus pdv. Du plus pdv. Okay. And if I substitute this in the second equation, I can write TdS is equals to dH minus vdp. Okay. So this is valid for both reversible and irreversible process, but for closed system. And this is valid for both again, reversible and irreversible process, but it is only valid for open system. Open system. Okay. Now we will use this formula to do the same thing what we did in PV diagrams. Okay. So you see, in order to draw, so this is my TS diagram. Okay. Now, can you tell me how can I draw a reversible isothermal process? A reversible isothermal process. Can you tell me? Yes, horizontal line. Okay. So I can draw it like this. Okay. So here temperature is constant and slope is 0. And I can also explain this, yes, parallel to entropy axis. I can also explain this by using ds dq is equals to t ds. Okay. Can I explain this using this? Yeah, I can. Okay. So you see, what will be the change? What will be the slope here? It will be dt by ds, right? This will be the slope on TS diagram. Dt by ds will be the slope. Okay. Now, because temperature is constant, so numerator change in temperature will be equal to 0, and therefore slope is 0. So dt by ds will be the slope. You see, I hope you remember, if we have PV diagram, the slope is what? By if you have y and x, so slope is what? Dy by dx. Okay, similarly, when we had PV diagram, so slope was dp by dv. Similarly, here the slope is dt by ds. So because temperature is constant, so dt is equals to 0 and the slope is 0. Okay. So I can also explain it like this. How about isentropic curve? How can I draw isentropic? Vertical, yes. So this is what I can draw. Entropy is equals to constant and the slope is infinite. So I can say slope, which is equals to dt by ds. Now here you see denominator is 0. So slope is infinite. But I have no idea how to draw constant volume and constant pressure process on a TS diagram. Yes, I don't know. So how do I figure out? I need to calculate dt by ds for constant volume and dt by ds for constant pressure. So how will I do it? I will do it by my combined first and second law equation. You see, we just now defined these two equations. Now we are going to determine dt by ds. Okay, so let's take this equation. So constant volume process, constant volume means this will be 0. So T ds is equals to du, and I can say that dt by ds, Tds is equals to m cv dt. Yes, so dt by ds is equals to T upon m cv. Let us assume mass is equals to 1. So ds is equals to T upon cv. So what is this? This is the slope of constant volume process on TS diagram. Okay. How about constant pressure process? So for constant pressure, I can use my second equation. Okay. So dH minus VdP, it should be minus. It should be minus VdP. Okay. So here, this is 0. So now TdS is equals to DH. TdS is equals to M Cp dt. So dt by ds is equals to T upon M Cp. Now let me take M is equals to 1. So dt by ds is equals to T upon Cp. So what is this? This is the slope of constant pressure process on TS diagram. On TS diagram. Okay. So let's come back here. Now I got this. This is how much? This is T upon Cv. This is how much? T upon Cp. Now tell me which slope is higher, which is lower. Slope of constant volume is higher or constant pressure is higher? Constant volume is higher. Very nice. Very good. Okay, very good. So as you can see, numerator is same, but Cp is greater than Cv. So because Cp is greater, therefore slope of constant volume will be higher and slope of constant pressure will be lower. So by this logic, can I draw slope of constant volume is higher? So if I say constant volume is higher, so it should be close to x-axis or y-axis. Constant volume, yes. So constant volume slope is higher. So I can draw something like this. Okay. So this is constant volume and slope is equals to T upon Cv. Okay. Next, I can draw constant pressure and it will be near x-axis. Now I know that you already know this. So it is x-axis. This is pressure is equals to constant and slope is equals to T upon Cv. Now you can see the slope is increasing like this. 0 Cp, sorry, Cp. Okay. 0, then this one, and then this one, and then infinite. Okay. It is increasing like this. Okay. So I can say slope of constant volume is greater than slope of constant pressure curve. Okay. So I hope this is clear. So now, so this is what we have written here: constant volume, constant pressure process. Okay. And whatever I wanted to explain here, I have explained you on this diagram. Okay, so this is how you can draw this. This is how you can draw this diagram. Okay, you can leave it. Okay, chalo. So again, I am really sorry. I need to cover so many formulas today, but there is no other way. Okay. So just to go ahead and see what we have discussed today's class. So this, whatever we have discussed, I explained earlier. Now then we have combined first and second law of thermodynamics and we got these two equations. TDS, this is valid for closed system and this is valid for open system. But they both are valid for reversible and irreversible. Why? Why is it valid? Because you see, temperature is a property, entropy is a property, internal energy is a property, pressure is a property, volume is a property. Every term in this equation is a property and therefore it can be applied to any process, reversible or irreversible. Similarly for this equation as well, everything is a property. Okay. So now slope of constant volume curve on TH diagram is this and slope of constant pressure, this is pressure. Okay, is this. Okay, and slope of constant volume is greater than slope of constant pressure. Okay, what else? This. So increase in entropy principle is what? Entropy generation or entropy of a process, entropy of universe or isolated system or system plus surrounding. For each and every one of them, basically change in entropy is always greater or equal to 0. So it is trying to tell you is that for it actually says that for a universe or system plus surrounding, Or what is the process? Process is also system plus surrounding. Okay, it always increases. It always increases. Now this is for a universe. Always increases is for a universe. What about a system? So system, we had reversible processes and we had irreversible processes. In reversible processes, we have seen that you always use this formula. Why? Because entropy generation is equals to 0 for reversible. Okay. So if you are adding heat, so entropy increases. If you are rejecting heat, entropy of the system decreases. If it is adiabatic, then entropy is constant. It is called as isentropic process. Okay. What about irreversible process? So in irreversible process, if you are adding heat, of course entropy will increase. If it is adiabatic as well, irreversible adiabatic, then also you see entropy is increasing. So it is no adiabatic is not a necessary condition for isentropic. You see, this is also adiabatic, but it is not isentropic. Entropy is changing. Okay. But when we have heat rejection, so entropy may increase, it may decrease, or it may remain constant. And this case is also called as isentropic. This case is also called as isentropic. Then we have seen entropy balance and closed system and open system. So this is for closed system, this is for open system. So all in all, whatever you thought that there are so many formulas, how will I remember it? How will I know which to apply, when to apply? So these two slides is basically summarizing everything. You need to know where these formulas come from. For that, you need to practice. You need to go through the lecture properly. You need to see how all the formulas are defined. And then very clearly I have mentioned, if you have system and isothermal, then you can use this. If you have a system non-isothermal and solid and liquid, then you can use this. Ideal gas, you can use any of them. Then you have these two formulas. So basically, I don't think I can make it simpler for you, simpler than this. Okay. So try to go through the lecture. Be very clear about how these formulas come, how we have defined these formulas, and then come back and see, or try to solve some questions and try to apply these. You try to identify these situations in the question. Are we talking about a system? Is it a reversible system or an irreversible system? If it is an irreversible system, then is it a solid or a liquid or a gas? Okay. So these type of things you need to work upon, and I think entropy would be a little easier for you. Okay. Now in the next session we will take up questions from second law and entropy, and I hope that you revise your entropy before that. So our next class is on Thursday. Okay. And you should revise entropy and second law formulas before that class, so that our discussion would be fruitful. You can ask good doubts. Okay. And whatever, like I want you to solve the questions, so that once you revise the formulas, when you actually revise, and then the second time you will get your revision when we solve the questions. Okay. So these concepts will become more, more clear to you. Okay. So I think this is it for today's class. Any doubt? Anyone, guys? Anyone? Any doubt from today's class or earlier classes? Yes, no. If you have no doubts, then at least say no. If you have doubt, ask me. Okay. So everything is clear. Huh? I taught so well, so perfectly, that you people have no doubt. Or you have not studied anything. That's why you have no doubt. Anyway. it doesn't matter. Okay, I have tried to give you the best. I've tried to explain. Yes, yes. If I yeah, yeah, sure, Subhendra, no problem. Revise. That's why I am asking you to revise so that in your next class you can ask whatever doubt you have and we can clear it then and there. Okay. So I'm very happy to see that if you people are revising and the things are getting clear. Also, do not just rely on the questions that we have done in class. Try to solve more and more questions from different sources. Okay, your previous year questions or whatever you have, or from a book or something. Okay. So, okay, I think we are done for today. I will see you in the next class on Thursday. Okay. Thank you. Thank you so much.